All right, we're going. I want to remind you a couple of things. Let's see, what day is today? Today is Tuesday. So I was there this morning. We're going to do something with some calculations that might make people uncomfortable. And so you need to be honest with yourself today after we go through these calculations. If there's parts of it you don't understand, you got to make sure you're asking me, because what we're doing today, I could expect you to do either on the quiz on Thursday or on the final exam that's coming up. Hi, Trinity. Okay, so just reminding you tomorrow, if that's your choice, that remains one of your choices to drop. I would talk to me before I did that, because most of you can finish this out successfully. And if you've invested all this time this semester, you may as well finish it out successfully. So we should talk about that. Our next lab will be next week. We're going to do a lab next week. Okay, so that's that stuff. Let me see. All right. Let's see. Here's where we were last time. Okay. And you're meant to remember. Let me plug in my stylus. You're meant to remember from last time that if you are dealing with concentration, that the key idea is that you have a ratio. It's a proportion of the part relative to the whole. And so if a concentration unit is given, I would rewrite it in that language of part relative to the whole. That's extremely important there. So I think we had done these last time, and one of the things we did last time was we took numbers like 5 over 250, and we said that'd be the same as 10 over 500, because if I want to compare this to that, you have to get them in a form that they can be compared to. This is 3 over 250 is the same as 6 over 500. Let me get Alexa. All right, Alexa, welcome. So I'm gonna shut up here for a minute and give you a chance to work through some of these other ones. Okay. So if nobody has any questions, what I want each of you to do is to answer C and D. Okay. Take a few minutes and get answers for C and D. So what was this one? This is 3 over 500. This one was 6 over 500. That was 5, 6, 7, 8, 9, 10, 11, 12. That was 12 over 500. This one was 8 over 500. And I can see from my list of people who's here. No fair leaving now. Now that I see who's here, because I might call on somebody, unless somebody wants to volunteer. Don't all respond at once.
Are you asking?
All right, yeah, I'm asking. Anybody wants to volunteer? I see Leela and Eli have their microphones turned on.
Yes.
So the one of you want to volunteer? Leela, you want to volunteer?
Yes. So I think solution B and solution E, they're equal. I mean, not equal, but same concentration.
Okay, so you say these two are the same concentration.
Yes.
Let me ask the whole room. Everybody okay with that?
Yes.
If you're not okay with that, you better chime in right now. Okay, I totally agree with Leela. I think she's right on the money. I think that E and B are the same. And I think this is an example of how you would not have arrived at that conclusion if you hadn't compared them under the right conditions. Okay. All right. So do we have an answer for D? If I mix E
out of 500.
Let me. I got to do the math. I got to get caught up. You guys are way ahead of me. Okay. So if I mix E and D, I'm going to mix 3 over 250 plus, which way am I mixing? E and F, rather. Oh, E and F. Okay, mix E and F. With 5 over 250. That would end up being 8. And I realize normally you don't add fractions, but we would get 500 mils total, right, in a solution. That's the same as which one? What'd you say, Eli?
There's a 16 out of 1,000.
Or it's 8 over 500. Do we have one over here that's 8 over 500? So if I mix these two together, I'm going to end up with a total of 8 red things and a total of 500 mils total. That's the same as which of those other solutions, A, B, C, or D? I got it written there. Dylan, you got an answer?
It's D.
It's the same as D, right? Isn't this the same as D? Everybody agree with that?
Yes.
Okay. All right. So here's my advice to you. I would work through these examples because I think the mechanics of working through those examples is good practice for working with solutions and working with proportions. And I'll be there for my Q&A this afternoon if you have questions, or by email. Okay, but I would work through the rest of those examples. I'm going to change gears now. All right. First off, how many of you have been to Hot Springs National Park? Hopefully everybody has been. Leela, did you go to Hot Springs before you left Arkansas?
No.
You got to go. When you come back, go to Hot Springs. Okay. It's definitely worth your time. I think it's the smallest national park in the United States. I think that's true. Anyway, if you go to Hot Springs, obviously what people go there for is they go there for the hot springs. And if you walk to the back, like behind one of the bathhouses, they'll have information like that. In fact, this is a duplication of the plaque that's etched in bronze on the rock behind the place. And so this is the kind of stuff that they would have written for what's in Hot Springs mineral water, okay? And these numbers are all in parts per million, okay? So what I would like to do, you and I are going to spend some time doing some calculations. Since we can't go to Hot Springs now because we're supposed to stay indoors, we'll do it virtually, okay? So if you need to feel Hot Springs when you get off the class, you can go take a hot bath and pour some salt in there. That'll be the same effect, okay? Idea number one. And I will give these to you on the test, but you got to know how to use them, okay? If you are aqueous solutions, and Hot Springs water is an aqueous solution, 1 part per million of stuff is the same as 1 microgram of stuff per liter. So if I was 1 part per billion of lead, that would mean 1 microgram of lead per liter. And just to remind you, 1 microgram, micro is 10 to the minus 6 grams. 1 part per million is 1 milligram of stuff per liter. So 1 milligram, just to remind you, is 10 to the minus 3 grams. Okay, just to remind you. Okay, so I got to ask everybody the first question right off the bat. Which of these two numbers is the higher concentration, or are they the same concentration? Is 1 part per billion more or less than 1 part per million, or are they the same as each other? If I had to drink water that contained lead, would I be just as happy drinking 1 part per billion lead, or as I would 1 part per million lead, or what would my conclusion be? Who's got an answer? Hey,
1
Madison.
part per billion is a smaller concentration than 1 part per million.
Right. This one right here is 1,000 times more than that. So if the number was 1, this one, if they were the same thing, this one would be 1,000 times more concentrated than that. And so part per billion is usually used for extremely low concentrations, and parts per million for low concentrations, but not quite as low. All right, do you have any questions? What I want you to do is I want you to get an answer for this, okay, in part per million and part per billion, and I want you to draw it from this chart over here. What is the calcium ion concentration in hot springs water in part per million and part per billion? I'll help you out. I get started. I think because it's that, I think the calcium concentration is 47.0 parts per million calcium. And the calcium that would be in hot springs water would be ions. And let's be complete, it'd be an aqueous solution. So write it like that. Okay. How about this one? And there's different ways to do this. So I'm gonna step over here just for a second. If I have 47 parts per million of calcium, and I'm required to write that in parts per billion calcium, first some concepts. When I go from this concentration, whatever this number is, would it be the same concentration? First question. If I was to re-express the calcium concentration here, would it be the same concentration or different? You can have your microphones off, but you got to at least chat. You got to send me something.
Different?
Okay, why do you think they'd be different?
Well, they're different units, right?
Different
So
units. So whatever number I put here will be different from 47. But if it's the same water here, same hot springs water here, as it is here, the same water, the concentration would be the same. It would just be expressed with a different number because the units are different. So Alexa, if you're getting at the fact that the numbers would be different, I agree with you. But the important thing is if it's the same water, the concentration would be the same, just expressed differently. Dylan, did you have a comment? Okay. All right. So one of the ways we can do this is we can take the information that's given. This is what's given for every million parts of the solution. And all I did with that was I just rewrote that, right? And Alexa, can you see my screen okay?
Mm-hmm.
Okay, I just want to make sure because I don't want to change it. Okay. And the idea is, this idea means that it's the same concentration. So I'm setting this ratio equal to the other ratio. The question is, how many parts of calcium would there be if I had 1 billion parts of solution? This will be that number, and this is that number. This is how we did it way back when, back in chapter 1 or chapter 2, when you and I were first doing this. And let me ask everybody, how do you solve for x on this mess?
Cross multiply.
All right, so I would have something like x times 10 to the 6th, which is this, equals 47 times 10 to the 9th. And I would solve for x by dividing both sides by 10 to the 6th. And I would get 47, 10 to the 9th, over 10 to the 6th. And what's the value for x then? If I solve this mess, these powers of 10 will cancel 3 of those left. Anybody got a number?
47,000.
47,000. thousand. And so what would this answer be? This would be 47,000 exclamation point. So it's 47 part per million. It's 47,000 parts per billion. Same concentration because the same water, but Alexa was right in that the number would be different. But it's important to appreciate that it's two ways of expressing the same concentration. So I actually want to ask, shoot, this is a good test question. Why don't they report these numbers in parts per billion? You know, this wouldn't say that. This would say 47,000 if it was parts per billion. Why not write 47,000 on there?
To make it seem smaller, maybe.
Or more manageable, right? Because
Yeah.
47,000 makes it sound like, oh my God, you know, this is awful stuff. And I have to tell you, 47 part per million of calcium is actually pretty high. And if you know anything about hot springs mineral water, you know that its mineral content is really, really high. Lots of dissolved stuff in it. But it makes it seem smaller. Was that Maddie who said that?
Yes, sir.
Okay, yeah. Okay, y'all okay with that? I mean, the only reason for reporting certain units on certain numbers is to make the numbers more manageable. This is the reason why when they report mileage between cities on highway signs, they report it in miles and not inches, because the number in inches would be a ridiculously large, unusable, unintelligible number. But if you report it in miles, it makes it a more manageable number that you can actually fit on the sign. And so part of the choice in how you report concentration units is just a personal choice to make the numbers more manageable, more understandable. Okay, how are we doing? So I would expect, given any of these numbers, that you could convert one to the next, parts per million to part per billion and back and forth. Okay. All right, let's see what the next thing is. Let's do that. I want to compare the chlorine level in Conway water, which is written, what do we do? Let's take the average, okay? Let's say this is our number. I want you to compare the chlorine water in chlorine level in Conway water to hot springs mineral water. Let's see. In other words, is Conway water more or less than hot springs? And here's the number.
Less.
Yeah, Conway's a little bit less, but not too much less, is it? I mean, the range, the upper part of the range has been almost as high as hot springs, right? So, yeah, it's a little bit less, not exactly the same. Any questions? Okay. All right. Now what I want to do is I want to do these two calculations. Okay. And if you're wondering, you know, what kinds of things is he going to ask on the quiz? What kinds of things could they ask about the final? When it comes to concentration units, these are those kinds of things. Okay. So it turns out, you don't have to know this, I'm telling you this. It turns out that Evian water, which is expensive drinking water, is 78 milligrams of calcium per liter. Okay. So let's do the first question. How does the calcium concentration in Evian water compare to the calcium concentration in hot springs water? Is it higher or lower than hot springs water, Evian? And just to remind you, remember what a milligram per liter is? A milligram per liter is the same as a part per million. How does the calcium in Evian compare to the calcium in hot springs water?
Higher.
Yeah, twice as much, not quite twice as much, but almost, right?
Mm-hmm.
You know, it's quite high, isn't it? And so if you've ever gotten hot springs water in your mouth, it probably has like a little bit of a salty taste. Evian would be even worse potentially with that taste. Okay. Let me ask you another question. What does the RDA mean? Do you remember on food what that means? Does anybody remember what the RDA is? They put it on my nutrition label. You can Google it real fast. What does RDA mean? Let's Google it real fast. RDA.
So recommended dietary allowance.
There it is. Okay. Per day, right? See how it says per day? Okay, so let's go back. Okay. So here's the first question. Okay, and I'm gonna give you some time to work on it. What I would like to know is, and this is all the information we need, I would like to know what is the recommended daily allowance of calcium in milligrams if one bottle, and this is one bottle, is 4% of the RDA. How many bottles of Evian do you have to drink in order to get your daily allowance of calcium in milligrams? So take some time and come up with a number. And there's 3 or 4 or 5 different ways to work this problem. I'm going to write some stuff down. 500 mils per bottle. One bottle, 4%, and it's 78 milligrams per liter. Okay, I got some stuff. RDA. We'll start with the basic question. How many bottles do I have to drink to reach 100%? Which would be my daily allowance. Let's see. 2 bottles will get me to 8%. Let's see. 4 bottles will get me to 16%. How much do I have to drink to get to 100%?
96 bottles. Would that be
Or okay, it's going to be high. Go higher than that.
higher than
In other words, we could actually set it up like this. You could say that one bottle is 4% of my RDA. How many bottles would be 100%? Because this ratio would remain the same, whatever is 4%. And so we could do the same thing. We could go 4x equals 100. And what do you get for x?
25.
Yeah. Okay. Surely there's an easier way to get our calcium, right? I mean, surely, right? Go eat some cheese and drink some milk. I think that's an easier way to get your calcium, because if you drink 25 bottles of Evian at 500 mils per bottle, you'll spend most of the afternoon in the bathroom. So, but at least you'll be well hydrated. That'd be good. All right. Everybody okay with the 25? 25 is what it's going to take to get to 100%. Okay. I'm not sure what to make of the silence. The silence, in my experience, usually means people don't understand. So you should ask me. If not now, then you should ask me sometime. Okay. I'm going to clean some stuff up here. Okay. Let me clean off some of this ink. I'm going to erase all the ink. Let's erase this junk. Okay. So what do we got? What I want is I want milligrams per calcium of calcium, right? And this is calcium up here. So 25 bottles. How many liters is that going to be? 25 bottles. Let's set it up like this. How many bottles per liter? 500 mils is how many liters? How many mils in a liter? Anybody with a Coke in front of them?
Is it 1,000?
Yep. So it's 1,000 mils is 1 liter. So 500 mils is half a liter. So there's half a liter in one bottle. That will cancel that. And somehow I've got to go from liters to milligrams of calcium, which is this piece of information that we haven't used yet. And so why don't y'all help me? I'll put liters on the top and the bottom here in order to make it work. In this fraction on the bottom. And what do I put on top?
Milligrams of calcium.
Yep. And how many is that?
78.
Yep. Let me see if this is going to work. This is 1 day, right? We already did that work down below. This is how many liters it's going to be. And if you drank that many liters, that's going to tell me how much calcium we would make. Who's got a number then? So what we need is 25 times a half times 78. Let's see. 25 times a half. Has anybody got a number?
975.
Yeah. Which is 1,000 milligrams is a gram. So apparently, I mean, shoot, that I didn't realize the number was that big, but apparently we get rid of calcium one way or the other. So we got to replenish what we've excreted. So, all right, before we leave this slide, I need some questions from people. There will be calculations on the next quiz and on the next test or final. All right. I want you to do basically the same thing. This time I want you to do it with hot springs water. How much hot springs water would it take to supply, what did we say it was, 975 milligrams of calcium? And just a quick concept, okay? Compare this number to this number. Will it take more or less hot springs water to do it?
More.
Why more?
Because it's a smaller number.
Yep, because concentration's lower. So you're going to have to drink more hot springs water. So you thought you were going to be in the bathroom for a long time after drinking all that Evian. If you do it with hot springs water, you'll be in the bathroom even longer. In fact, you probably would never leave. They just keep passing the bottles through the door. Okay. But at least you have your calcium, though. That's good. All right. I want a number. Work this out. I'm going to give you about 3 minutes to get a number. And in case you need a reminder, remember that 1 part per million is the same as milligrams per liter. So if I'm 47 part per million, that's the same as 47 milligrams of whoever the guy is for every 1 liter of that solution. Okay, that's the idea. All right, a few more minutes. Couple more minutes. Hopefully you got a number that makes sense to you. And you told me that we would need more Evian water. Or I'm sorry, more hot springs water to do it. I mean, there's lots of ways to work this problem, but I'm thinking I'm going to start from here because this is how much I need. And I'm going to finish with liters of hot springs water. So somehow this is connected to that. So if I was to set this up, somebody help me. Do you want milligrams to stay or go?
Go.
Okay, so Alexa, does that go on the top or the bottom?
Bottom.
Okay, so I'll put milligrams of calcium down here. And I want liters of hot springs water to come in on the top. Now I need numbers here. What numbers do I put where? Something about this number. What goes where?
Milligrams of
Yeah,
calcium.
so the 47 goes top or bottom?
Bottom.
Yeah, because this is the same as parts per million, but inverted. I want y'all to be convinced of this. If this, I do this and this, I don't know, what does that math turn out to be? It's a lot of water. Anybody got a number?
I got 20.7.
Oh my gosh. Yeah, that's what I got too. So 20.7 liters, exclamation point, which is, if you divide by 4, that's about 5 gallons. So you'd be drinking a lot of water. 5 gallons of water, you'd be really hydrated. Okay, any questions here? Because we're going to add something new. This is meant to be practice. And there's the way that I did it is not the only way these can be worked. These can be worked different ways. This is just one way to work it. And you'll see other examples written out in the book, I think. Okay. So what concentration units do you have to be familiar with in chapter 8? You got to be familiar with this one. You got to be familiar with this one. And then you also got to be familiar, because we're in a chemistry building virtually, you got to be familiar with this one. Okay. And so this is a new concentration unit. It's a concentration unit that we got to have before we finish this semester with an idea called pH. And pH, I know, is something you've heard of. They talk about it in advertising. I'm not sure people quite understand what it means, but you will at least hopefully have a little bit of an understanding. And to do pH, you got to do this concentration unit called molarity. So molarity is a concentration unit, okay? It's part over the whole. And so I'm just going to offer this without proof, all right? This is what it is. It's moles of stuff. So if I was doing calcium or lead or whoever in Hot Springs mineral water, I'd have to convert my grams to moles, okay? And the amount is always liters of the whole thing, okay? And so molarity is the moles of calcium per liter of Hot Springs mineral water. The molarity of lead in Conway water is the moles of lead per liter of Conway water. And let me ask everybody, how did we get moles in previous chapters? What do we have to get moles? You got to remember this.
The mass number?
Careful with the mass number. I'm going to call it the average mass from the periodic table. Remember that number? The mass number is an integer number. The average mass number that would be written on the periodic table is the grams for 1 mole of whoever that guy is. And so I'm assuming that everybody remembers how to do the molar mass of something to pull those numbers from the periodic table. All right, let's see what I want to do then. Let's go back and let's do this one and let's do this one in Hot Springs mineral water. All right, let's just do them one at a time. Let's just do magnesium. What do we got? We got 4.9. All right, so let me get some room here. All right, so we want the molarity of magnesium in Hot Springs water. And Hot Springs water is 4.9 parts per million of magnesium. And what I would like to know is I would like to know how many moles of magnesium for every 1 liter of Hot Springs water. That's what I want to know. Okay, what do we do first? What'd you say before? I think that was Maddie who said that. Maddie, what do we need to solve this problem?
The mass number?
Careful, don't call it the mass number.
Mass.
Yeah, do you know why I'm giving you a hard time, Maddie? Because mass number is that number for an isotope, right?
Oh.
And that's not exactly equal to the red number on the periodic table, right? So I want to be careful not. I mean, it's close to that number, but it's not exactly equal. So I agree with what you're saying, but I think what I'd rather say is the average molar mass, the average atomic mass off the periodic table. Okay. All right. So be careful there, everybody. So what's that number for magnesium then? I don't have a periodic table in front of me. Who's got one? Got their book out. What's the number for magnesium? Magnesium's under calcium or above calcium on the left.
24.31.
20.31, and the units on that guy is grams per mole. Okay, there's grams. What part of this is related to grams on the whole slide? So when you're alone on a test or a quiz, there's some part of this that you have to know that's related to grams. What part?
Parts per million.
Yeah, okay, so what was that? 40.9 parts per million is the same as 4.9. Do you remember which one it was?
Milligrams.
Yep. And I would give, I just want to remind everybody, so it's kind of set your mind at ease. Okay. On the front of the test, I'll write this down. Okay. So in case you forget, and I'll write these conversions. But you do have to know that those guys are related to grams. That's a concept you have to bring with you. Okay. So this is the same as 4.9 milligrams of magnesium for every 1 liter of Hot Springs water. And hey, take a look. Isn't this already that? So I only got one thing to do then in order to make this the same as that. Well, what do I still have to do then? This information up here. In other words, there's something else I got to put in here. Let's just do it in steps. Do I want milligrams to stay or go?
Go.
Yeah.
Okay, so you guys are experts. Where does milligrams go in my fraction if I want it to go?
The bottom.
Uh-huh. And I want milligrams to become grams, right? Because if it was grams of magnesium, then I could use this information to go to moles. And anybody remember which one's larger? A milligram or a gram? If you're going to eat a milligram of poison or a gram of poison, which is more dangerous?
Gram.
Gram.
Yep. So 1 gram is 1,000 milligrams. Okay. So that's good. So my milligrams will cancel. And remember, we want to keep that, right? Because that's down here, so I want to keep it. Okay, I got one more step. One more step to do. You want grams to stay or go in my final answer?
Go.
Okay, top or bottom?
Bottom.
Okay, grams. And what I want that to become is I want that to become moles, right? Moles of magnesium. Okay, so what numbers do I put in there? Where does this go?
The bottom.
Yeah, because it goes with grams. And that goes on top of moles, right? Now I need somebody with a calculator to grind all this mess out. But when I get the whole darn thing, I'm going to be ending up with moles of magnesium. And the 1 is still there. That'll stay there the whole time. Who's got a calculator? 1 liter of hot springs water. Who's got the number? Be 4.9 times 1 times 1 divided by 24.3 divided by 1,000 divided by 1, whatever that is. Do we have a number? Who's got it? Maddie, do you have a number?
I got 0.0002.
Okay. I could expect that when you do all this, it's probably a small number. So that seems not unreasonable then. And if you can see, this is a crazy, stupid small number. So it makes more sense on a plaque to use numbers like this because people can sort of wrap their head around it. This is a number that if you put it on the plaque, people wouldn't stay around to read it. They just keep moving. But in the world of chemistry, things have to be in moles, especially if we do things like pH later on. And so this is the reason we've got to do this. Are any questions? Because what I'm going to do now is I'm going to go back and I'm going to turn you loose. I want you to do the same thing we just did, okay? But I want you to do the same thing, but now for bicarbonate. Bicarbonate, there's the number for bicarbonate. Do exactly the same thing we did and tell me what the molarity is for bicarbonate. And I'm going to give you 3-4 minutes, long enough to go get a cup of coffee, and I'll come back. All right, so get the number for bicarbonate. So this should feel just like what we did before, where this is 1, that's 1,000. This is this. This is this. I need a number here. What number do you put there? Because I can't find bicarbonate on the periodic table. So how do you get the molar mass of bicarbonate? What'd you do, Maddie?
You add up all of their masses.
Right. So hydrogen is 1 gram, right? And carbon is 12. And 3 oxygens is 3 times 16. What'd you get when you added all that up?
61.02.
Okay, 61. I'm just going to round it off. Is that okay?
Yes.
All right. So where does the 61 go up here?
On the bottom.
Okay, so every 1 mole of bicarbonate is 61 grams. So whoever this guy is, this part of the calculation will be different depending on the numbers that you get from the periodic table. And when you grind all that out, what do you get? Which would be
0.002.
0, 0, like that again?
No, just 2 zeros.
Oh, whoops, okay. 0.002 molar. And so they would shorthand it, moles per liter would be M bicarbonate. And so which one's got a higher concentration, bicarbonate or magnesium? In hot springs water. Higher, which one's a higher molarity?
Bicarbonate.
Yeah, by a factor of 10. Yeah. And so the bicarbonate that's in hot springs water can come from dissolved carbon dioxide. It comes from dissolved minerals and other sources. Magnesium only comes from one place, and that's from the rocks. And so there's only a limited amount of magnesium in rocks. All right. Let me see what I got. I got exactly that same number. Okay. So this right here in scientific notation is 0.0002 molar magnesium, what we had before. I got the same number. All right, let me answer any questions. This is supposed to remind you using the periodic table to get molar masses and all that kind of stuff that we did before. Okay. And as I said, I would give you the definition of molarity. I'll give you the definition of parts per million and parts per billion, but you got to know how to use them. Okay. All right. Now, you and I are going to change gears a little bit. Okay. And one of the things we're going to do is we're going to spend a little bit of time talking about some of the compounds that are dissolved in water. And this is meant to be like a little bit of a review. You may remember that compounds can be ionic or covalent. And do you remember the difference between them? Let's say I'm down here and I'm reading all these. How do you know if something's ionic from this list? And how do you know if something's covalent from this list? Who can remember the definitions and how I keep these straight?
Ionic is non-metal plus metal.
Let me write this down. Non-metal plus a metal tends to be ionic. And what about covalent?
I think it's non-metal plus non-metal.
Right. Two or more nonmetals tends to be covalent. And metals and nonmetals tend to be ionic. I totally agree with that. Okay. So I don't care that you know the formulas of these compounds. I would never ask you to memorize that. But I do want to ask you one question. Let's do this. Find over here in this label a ionic compound. Do you see anything over there that looks like it? You would bet your life that it's ionic. Anybody in here looks ionic to you? This is the stuff in a multivitamin. I know what I'm going to do. If we were sitting in class, I'd be calling on people. So let's see. Don't leave yet. Don't leave class. Okay, I see Elizabeth is there. Okay, let me check my list. Okay. So Elizabeth Sperry, I'm going to ask you to give me a choice. Who else is there? Madison May, you can give me a choice. Patrick, you can give me a choice. If your microphone doesn't work, you can text your answer. Find an ionic compound over here that you're sure it would be ionic. And the key thing is, if you find anybody over there that's got a metal in it, then I would bet my life that it's ionic. Elizabeth, do you have an option?
Yeah, would the pyridoxine hydrochloride be one?
Which one is it? Where is it? Is it the bottom or the top? I can't read it.
At the top, it's the second.
This one right here?
Mm-hmm.
Okay, it's interesting that you said that. That guy's not a metal. I don't even know what that is. That's some kind of who knows what. Elizabeth, the answer to your question is yes, that's ionic, but not because it contains a metal. And so so it won't be clear to anybody in the room why that's ionic. But she's right. Who on here who's a metal? Madison or Patrick? Who's a metal on here? Do you see a metal on the list? If you don't remember, you got your periodic table. I see 4 of them that have metals in them to me. Madison, you got one? Patrick?
Is silicon dioxide one?
All right. But look at you guys are working hard, man. You're working too hard. Okay. That one's on the edge. This is one of those metalloids. Pick somebody else. Is sodium a metal or a non-metal? Hey, class, is sodium a metal or a non-metal?
Non-metal.
Sodium. Did you have a periodic table? Get your periodic table out.
It's a metal.
Yep, that's a metal. So whatever this is has got to be an ionic compound because it's got sodium in it. Anything else here that's a metal that you can tell? This sounds like a good test question. Anybody else? Because I'm going to go start looking in my cabinet to find labels, and I'll just scan. Anybody else here that's a metal?
Calcium.
Yeah, isn't this weird guy right here, whatever that is, a ionic compound, whatever it is? Anything else?
Magnesium stearate.
Yeah, whatever that is. I have no idea, but that's what that is. Okay, and we got any more? Madison? Madison May? Maddie? Is it Madison? Yeah, Madison May, you got one?
I was gonna say the magnesium stearate.
All right, good. That one's okay. Any other ones that you see? Elizabeth picked the hardest. Okay, I would not have picked that one, Elizabeth, but turns out you were right. Okay, for reasons we won't go into. Anybody else? What about that one? Metal or is that ionic or covalent? You figure? What do you think? Ionic or covalent? This compound?
Ionic.
Yep. Okay. So don't overthink it. There was a big pregnant pause, like people were worried about giving the wrong answer. If it's got a metal in it in this class, I would bet my life that that compound is ionic, right? And the reason why that's important as we go further is it governs what you do when you have those things dissolved in your water. Okay, it affects the properties of it. Okay, so you and I are going to go down a list. How is a compound different from an element?
It has multiple.
Has multiple elements.
Okay, which one has multiple elements?
Compound.
Compound. Okay, so a compound is a minimum of how many? Minimum.
2.
Okay, let me write that down. It's a minimum of 2. Okay, let me try another one. How is a molecule different from an atom?
It has 2.
What has 2?
The molecule.
2 what?
2 atoms.
Okay, at least 2?
Yes.
Could a molecule have more than 2? Could I have a molecule with like 5 atoms?
Yes.
No problem. Yeah, I mean, you've got molecules can be huge with lots of atoms in them. Okay, so a molecule is a combination of a minimum of how many atoms? Minimum.
2.
It's got to be 2. Okay. All right. Can you have a molecule of a compound? Can you have a molecule of sugar, a molecule of aspirin, a molecule of hydrogen peroxide?
No.
Yes.
Hard yes and no. Which is it? Does that make sense? A molecule of sugar, a molecule of aspirin, a molecule of carbon dioxide? We can totally have that, right? So a molecule, like CO2, like water, these are all molecules, right? And those represent compounds, okay? Can you have an atom of a compound? Can I have one atom that represents a compound? Is argon a compound?
No.
No, it's got to be 2 or more different elements, right? And this is only one atom, and that could never ever be a compound. Okay. All right. So one atom cannot represent a compound. You got to have at least 2 atoms, and it's got to be more than one kind of atom to be a compound. All right. All right. Last question before we do some examples. How is an ion different from all the rest? In other words, an ion is like this, and all the rest of these are like this. Something about an ion that makes it unique.
It has a charge.
Which one has a charge?
Ion.
Okay, this guy has a charge, and these guys are all neutral, right? So this has no charge, this has no charge, that has no charge. But if I had carbonate ion, this thing has a -2 charge, okay, and that would be something different. So the difference is ions have charges, okay, and cations, which one's positive, which one's negative, cations or anions?
Cation is positive.
Yep, because it's got a T in it. That's how I remember it. Okay. All right. So now I'm going to ask you about the 2. What does that 2 mean right there? Like if I write that formula, what's that 2 mean?
Fluorines.
Okay. What does that 2 mean?
2 fluorines.
Okay. What does that 2 mean?
Two fluorines.
Same thing, right? Okay, it's like a broken record. Okay, let's go back up here. If I asked you to describe this to me on a test, compound or an element, what would you say?
Compound.
Okay, write that down. This is the compound. This one, what would you say?
Element.
That's an element. Okay, wait a minute, but it's got two. Why are we saying element and not compound here?
Because it's two of the same element.
Yep, it's got to be different, right? Okay, what would you say down here for this example?
Compound.
Okay. Now I want you to go back and I want you to use those words. Ionic or covalent. This compound is ionic or covalent. I would bet my life. Top one.
Ionic.
Vote for ionic. Why would you vote ionic?
Because it has
It's a metal and a non.
Metal and a non-metal. Okay, what about this one down here?
Covalent.
Okay. And the reason why we're bringing this up is the behavior of ionic compounds in water and the behavior of covalent compounds in water can be different. And so part of knowing how they behave, and this is related to something we mentioned in chapter 7, when you and I talked about electrolytes, this is related to that. And I'm watching the time. We got about 13 minutes left to go. Don't forget that tomorrow there will be a graded assignment posted, and I'll be available for Q&A tomorrow instead of lab. That's what we're going to do. Okay, it'll be not a long graded assignment, but it'll be one nonetheless. All right. So I want to go through this example. That's a molecule, right? This is fluorine, and this is the oxygen right there. Okay. That's a molecule where it's got two fluorine atoms. And if I asked you, but I'm not asking you, to draw the Lewis dot structure, you would draw the Lewis dot structure. This is something a little different. Those are molecules. This is two separate ions. Okay. Do you remember in chapter 7 when we were talking about separate ions? In what context we were talking about separate ions? What idea from chapter 7 is related to ions that are separated? Part of a battery, part of any battery. This is the reason why you don't toast toast on the side of a bathtub. This is the reason why you don't blow dry your hair on the side of a bathtub. What idea from chapter 7 was related to separate ions?
Electrolytes which travel. They're mobile.
Right. So remember the idea from before, okay? It's when the ions are separate that they're free to go. Fluorine can go this way, calcium can go that way. These molecules got to go around together. This molecule's got to float around together. These are separate and able to go in different directions because they have different charges, okay? And so that idea is a really important one in that case. So I got a cartoon to show it, all right? Let's say this is something like sugar, okay? This is sugar molecules. And if you had a crystal of sugar, you would see individual sugar molecules close to each other and they would be in some pattern. Well, this would be like an ionic compound where you'd have anions and cations, and they would close together and they would be like this. So apparently this guy is an electrolyte, and apparently this one's a non-electrolyte. So I'm gonna show you the cartoon, okay? Ready? Let's watch what happens when each of these crystals dissolves. Oh. What's different? What was different? This guy right here has a charge. Does this have a charge? It's a molecule.
No.
Yeah, these are little things that have no charge. And sure, they're separated from each other, but they don't have a charge. And so as a result, there are no charges that can move. And this guy is a non-electrolyte. It could be water soluble. It could break down into little parts. But the parts, when they're separated, don't have charge. And so a solution like this will not conduct electricity. On the other hand, An electrolyte, which is what you get when an ionic compound falls apart. And the $10 word that means falls apart is called dissociation or disassociation. And that's what electrolytes do when they're dissolving in a glass of water. And so what about this guy? This ion can go this direction. This ion can go this direction because it's positive, and you would expect the negative guys to go in exactly the opposite direction because they're negative. And so because they're no longer encumbered by being attached to ions of opposite charge, holding them as a crystal, they're mobile and free to move. And anytime a charge can move, that's what we would call an electrolyte. It's capable of conducting electricity. Sugar, even though it's mobile, has got no reason to move because it's not influenced by positive or negative charges because they have no charge. All right, so a very important idea right now, take-home message. You got to know what they mean by the dissociation of an ionic compound. That's an ionic compound that breaks down, and the context would be when they become electrolytes. And something that's a non-electrolyte might break down, could be nicely water soluble, but it breaks down, breaks apart into separate uncharged things. These are just molecules that have no charge. All right, so we already talked about this, okay? So let's do some periodic table practice. Are there any guys on here that you figure that are probably ions? Calcium is probably an ion in water. Magnesium is probably an ion. Sodium is going to be an ion. Potassium is going to be an ion. How in the world do you know what the charges are? How do you know from the periodic table what charge things have? So in other words, how do I know that fluorine is a -1?
Because it wants to gain 1 electron in order to be like the closest noble gas.
Who does it want to be like? Look at your periodic table. Who's the closest noble gas to fluorine? Which noble gas is closest?
Neon.
It wants to be like neon. And you're exactly right. Fluorine's got 9 electrons. If it gained 1 more, it'll become like neon. Who's the closest noble gas to calcium? Which noble gas is calcium trying to emulate? Anybody out there with a periodic table? Which one?
Does it want to be argon?
Yeah, like argon, because argon is the closest. It's kind of hard to see because it's on opposite sides of the periodic table. But if you check the numbers, calcium's got an atomic number of 20 and argon's 18, and so it's 2 more. So if calcium loses 2 electrons, it'll become 2+, and it'll become like argon. So let's go down our list. What charge is calcium going to have? Calcium is going to be +2. What charge is magnesium going to have in hot springs water? Look at your periodic table. You got to know this. You've got to be able to assign charges to these ions. What charge will magnesium have? Look at your periodic table.
+2.
What about sodium and potassium? What about those guys? Sodium will have what charge in hot springs water?
Sodium has +1.
+1. What about potassium? Same family. What about potassium?
1.
All right, let's jump to the other side. What about these two guys? What are their charges in hot springs water? Chloride and fluoride.
1.
Okay, 1 negative or positive?
Negative.
Yep, -1. Okay, pop quiz. What about the charge of oxygen molecules in hot springs water?
-2.
Good, don't bite on that. No charge, right? Did y'all see why it's no charge? Because they're talking about the molecule. If they were talking about O by itself, it might be 2-, but that's not what they're talking about. So a molecule has no charge. What's the charge on a carbon dioxide molecule in hot springs water? that guy like oxygen will have no charge. Anybody that's a compound will have no charge. But now these two guys, you all may remember, okay? Bicarbonate is one of those ions you memorized. He has a charge. Sulfate is one of those ions. They didn't write it on the plaque, but he's got a charge. You remember the charges? And there's no way to know this except to memorize these, which is why I had you memorize them earlier. What's the charge on bicarb?
Negative.
Yep. And what about sulfate? Do you remember?
-2.
Yep, 2 negative. Okay. And so I just want to remind you that you're going to know the charges of this family be +1. This family is +2. This family is -1. And if it's O by itself, it'll be 2-, but not part of the molecule. Nitrogen will be 3-, and there's no way you're going to know what these charges are. We'd have to tell you what those charges are, and we're going to do some examples on that next time. Okay. When you're on the edges, you know what the charges is. Aluminum will always be 3+ because it's 1, 2, 3 away from neon, which is the nearest noble gas. So aluminum will always be +3. Okay, don't try to make sense of why these charges are what they are. It's more than what we can do, okay, in this class. So we'll pick that up next time. But before we end, though, I want to mention a couple of things. Let's see. Back right there. Back. All right. So where are you gonna find the details on your graded assignment? It'll be posted right here. Okay. So sometime later today, certainly by tomorrow, well before 2 o'clock. I'll be there at 12. Okay. And so I think what I'm going to do is I will be available for Q&A by email. So if you want to talk to me, shoot me an email, and we'll set up a Google Meet and we'll work examples if you want to. Okay. So I will watch my email from 12 to 2, looking for emails from me if you have any questions. This graded assignment will make we got a quiz on Thursday. I think what I'm going to want to do is I'll probably make this graded assignment due next Tuesday is probably what I'll make it. I'll set it up that way. Does anybody have any questions before we call it a day? I will be, let me see, what, Wednesday. Don't I normally have Q&A on Wednesday? Wait, what day is today? Tuesday? Normally on Tuesday, I got time in the afternoon. I think, is that right or wrong? I don't know if that's true or not. Let's see. No, Tuesday I already had it this morning. Okay, so my next Q&A office hours will be 8 o'clock tomorrow. Okay. All right, I'm gonna see y'all later. Take care.
What time is the assignment going up tomorrow?
Before noon. Okay, I'll try to have it up today, but it'll certainly be up there before noon tomorrow. Okay.
Okay. Do you want to do at the end of when lab would be?
No. What I said was I thought because there's some work I want you to do on the internet with it. It won't be super long. Probably the total time commitment is about 15 to 30 minutes. Okay, but I'm going to want you to use some stuff off the internet to answer the questions. Okay, so I'll give you time to search some things. So I'm going to give what I said. You may not have heard me, Eli. So I'm going to try to probably give you till next week, next Tuesday, to hand it in. Okay. All right, y'all. All right. Take care.